So we're the plan today is to take 10-15 minutes of questions, and then we'll do this homework quiz and kind of get out of here. Sound good?
Yeah.
Okay. Is this all ready for questions?
Yeah.
Okay, fine, no problem. Elvis, what's up?
47.
40. Which one?
47.
47? Sure. Oh, I didn't grab that page. Grab it real quick. Okay. Oops. .47 says, this is the lawn dart one, right? Yeah, standing 15 feet in front of an 18-inch diameter circular, 15 feet from the front of an 18-inch diameter target, okay? So here I'm just going to sketch out a little bit of a picture. So there's 15 feet. And then we have the front of a circular target. So 18 inches is 1.5 feet. It's on the ground. You throw a lawn dart in the direction of it. You release that dart 5 feet above the ground. And release at an initial velocity of 70 degrees with an angle of 70 degrees. And will the dart hit the target? Okay. So I'm going to start by writing my parametric position function. So x of t is initial velocity, cosine theta times t. And my y of t is going to be negative 16 t squared plus initial velocity sine theta t plus the initial height. And what I want to know is this point, basically. I want to know the x value when the y is 0, right? That'll be when the dart hits the ground. To do that, I want to find the t value associated with when y is 0. And I'm going to take that value for t and then plug it back into my x. So to solve this for t, this is a quadratic equation, so I'm going to plug it into the quadratic formula. Okay, so fire up my calculator here. I'm going to use alpha and y equals to use the fraction command to type this in. So negative 30 sine 70. Note that my calculator needs to be in degree mode when I'm doing this because the angles are in degrees. I can't type the plus or minus into my calculator, so I just would do it one at a time. I already know from doing these problems that it's the minus one that I need. So I'm going to type the minus. And then 30 sine 70 squared, I'm going to put a parenthesis around that because both the 30 and the sine 70 both need to get squared. So I do that, I get 1.92 for t. So the dart's basically in the air for 1.92 seconds. So then I'm going to do x of 1.92. And that'll tell me how far horizontally the dart went. So that's 19.7-ish. And if I look at this, my picture up here, 15 feet to the target. The target's 1.5 feet. That was a diameter, right? Yeah, so 1.5 feet all the way across it. So it's 16.5 feet to the end of the target. So I've missed the target by, 2 or 3.2 feet. Oh, 2.2 feet. Because this is greater than 15 plus 1.5. Does that feel okay, Elvis? Luke? 44C? Sure. Okay, so here Matt hits a baseball when it's 3 feet above the ground with an initial velocity of 115 feet per second. The ball leaves the bat at a 41-degree angle with the horizontal and heads towards a 20-foot fence that's exactly 385 feet from home plate. Will the ball clear the fence? If so, blah, 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 blah. Okay, so again, write our parametric function. This is what you're asked to do in part A, so I'm just going to copy that down real quick. Okay. So the idea here, if I draw a little picture of what's going on, so here we have the ball at the initial 3 feet off the ground. We hit it. It's going to go over here. And we're concerned about this point, right? Specifically the y coordinate at this point, which will tell us like how high that ball is. So I know we've gone 385 feet to the fence. So the x coordinate is 385 there. So I need to find the value for t when the x is 385. To do that, I'm going to take my x equation, plug 385 in, and solve for t. Since that's a linear equation, all I need to do is divide both sides by 115 cosine 41. Cool so far? Have to be a little bit careful about typing that into your calculator. I'm going to use the fraction command so I don't have to worry too much about my parentheses. And I can just type it exactly like it looks on my sheet of paper. So when I do that, I get about 4.44. So then all I need to do is y of 4.44, and that'll tell me the height of the ball at that point. And then I can compare that to the 20 feet to tell whether we made it or not. Does that feel okay, Luke?
Yeah.
So 22.8 feet. So that's a home run by 2.8 feet. Since that's greater than 20. So we made it. Squeaked her over. Surge.
Can you just do like any limit parameter with like a quadratic?
So yeah, I'm going to combine this with Eddie's because he was asking about something similar to this. So which one were you, Eddie? You wanted to like modify one of these, right?
You can do 24. You can just do 3t squared plus 2t plus 2.
Okay. So we're just going to have a modified version of this problem. 3t plus 2t, you said, plus
Yeah.
2? That's fine.
Yeah.
And the y can just stay the same? Okay. Okay, so if you want to eliminate the parameter on something like this, it doesn't really matter whether you want to start with the x or the y. It's whether you want to deal with the quadratic part when you get the t by itself with using the x equation, or if you go the reverse, you'll have to get the y by itself when in the Cartesian equation. Either way, you'll be dealing with a quadratic, so it's not like it's 6 and 1/2 dozen the other when you're going to deal with it. Which one do you want to do? When do you want to deal with it here?
Deal with the quadratic now.
Okay, so we're going to get the t by itself using the x equation. That's probably what I would prefer to do. So to get the t by itself, basically I need to solve for t, right?
Yeah.
So to solve a quadratic equation, it needs to equal. Yeah.
Why wouldn't you start with the y? Because then would t just be 2 and then you just plug back into the x?
It would be 2y.
2y.
And then you're going to have the same problem we're going to deal with right here. So it's whether you do you deal with it now or then, it's going to be the same problem. It's got to equal 0, right?
Yeah.
Okay. So I'm going to subtract the x over to the other side. So it's equal to 0. Okay? What are the ways that I have to solve a quadratic equation now? Quadratic formula is the one that I would want to use here because factoring is not going to help me get the t necessarily by itself in one place, and completing the square would be another one I could use in this case, but that's like as bad or worse than the quadratic formula. Let me just use the quadratic formula. So in this case, the a is 3, the b is 2, and the c is going to be 2 minus x. Is how we would treat that. And so I'll just simplify things down now. So I have 4 minus, let's see, that's negative 6 times 2 is negative 12. And then negative 6 times negative x is positive 6x. And then 6 in the denominator. 4 minus 12 is negative 8. So there's my t by itself. It's in terms of x, which it should be.
Wait, 1 second. So how did you get so you took negative 4 times 3.
Mm-hmm.
And they took that value multiplied by 2.
I distributed it. So I just took that and distributed through.
3 distributed through, and they multiply that. Then you multiply that number by 4 as well.
Oh, did I do? Oh, yeah, sorry. I just goofed. Yeah, so the arithmetic was just wrong. Yeah, sure, thanks. So 24 and 12x. Right? That's what we're complaining about, which is a legitimate thing to complain about when your math teacher boogers basic arithmetic, and it's confusing as to like what you did because you just multiplied by 2 instead of 4 or something when you're trying to do your mental math, which gets confused. It's confusing from your seat. Yeah, it does, right? Okay, we're all okay? Okay. And then now, since the t bytes is by itself, I can just drop that into the y equation. Now, I guess I could simplify that a little bit, but I'm not so worried about it. Again, inside the radical, could I pull off a factor of 4 and then square root that and reduce the fraction a little bit? Yeah, I guess, sure, whatever. But we did the hard part. Is that okay?
So you just took that number and multiplied and multiplied by it.
Well, I multiplied the two fractions, right? So I multiplied the top part by 1, stayed the same. The bottom part by 2 becomes a 12. Is that cool? Does this part affect doing the domain and range pieces though? No, man, you should be able to do that regardless of how difficult eliminating the parameter is, which sometimes it could be really difficult. It could be much harder than this even. But, you know, even so, the domain and range parts are usually things that are pretty doable. Eddie?
What about the plus or minus part?
Well, that doesn't matter to us because we're not using this function to do the domain and range.
Oh,
Right?
you're right.
We use these guys. So we're still doing -8 to -3 for the parameter.
Yeah.
Okay. So the domain here is from the x of t function. So since that function is quadratic, there's 3 points we're going to care about. So the vertex and the 2 endpoints. So the vertex is going to be -b over 2a. So that's -1/3. And since that's not inside the interval that we have, we don't care about it. So all I really need to do is x of -8 and x of -3 and build it out the same way I would normally. It's okay. Yeah. -b over 2a.
Then the range and plug in. That's the y.
Since the range is linear, it's just the endpoints is all we need.
Yeah.
Yep. Luke? Yeah. So I mean the same idea. You could graph this because that's really what we're talking about, right? So like, you know, it's going to be to like -3 is going to be like here, and it's going to, if you kept going, I don't know. But you just have a piece of it. So sometimes looking at the graph, like getting your calculator to just graph a piece of it. Yeah. Jake? So depending on what the answer to that question is yes. You could do either one. So you could graph it as a parametric altogether, or you could graph in function mode just the x of t equation and look at what's going on. Either is appropriate. Taylor?
Do we have to find the vertex first, or can't we just plug it in the equation to begin with?
So the answer to that would be like depending on how picky the directions were being. So like if they're asking you to like show the domain as blah blah blah, like a picture is not really an appropriate response to show. Like that's asking for a little bit more proof, where doing this where we've actually analyzed it and been like, hey, here's the, you know, here's the vertex and it's not in there, so the only thing I need is the endpoints because I know my function is all increasing or decreasing over the interval.
So right now, we're finding the domain, right?
The domain for the Cartesian function, yes.
Yeah. So to do that, you just plug it in, like plug in the given, like the -8 and the 3 to the x equation, right?
Because the vertex doesn't matter, yes.
We only do that when the vertex doesn't matter?
Yeah, let's say that this number instead was like 10, just say hypothetically. Nope, that's not big enough. Let's say it's 30. That's big enough. So if I do that, then this would be -5, which is in there. So I'd also have to look at x of -5. Because now what's going to happen is you're going to have something like that going on, where the actual minimum for the function is not one of the endpoints. You know what I mean? So we do need to check the vertex there, because it could be one of the endpoints for the domain or range, depending on what you're working on. Does that make sense? And the reason it can play is because, like, we have a change in whether the function is increasing or decreasing if the vertex is in between the endpoints. If the vertex isn't in between the endpoints, it's either all increasing or all decreasing. So, like, all that matters are the endpoints. But when you have a change like that, you're going to get potential problems. You know what I mean? All right. Let's do this thing, right?